Hey everyone! Today, we're going to unlock some secrets of the past using one of the most incredible scientific tools ever invented, radiocarbon dating. Now, this thing has basically allowed us to put a calendar to prehistory. But as we're about to find out, this clock, well, it doesn't always tick as steadily as we once thought.
So think about it. When an archaeologist digs up something amazing, like the Dead Sea Scrolls, how can they look at it and say, with any real confidence, yep, this is about 2,000 years old? How do they read that invisible clock that's hidden deep inside the artifact itself? Let's dig in and figure it out. Well, the answer lies in a truly brilliant idea. It's a concept for a clock that's not made of gears and springs, but of the one element that forms the basis of, well, all life here on Earth: carbon. So this whole method got its start back in 1950. It was developed by Willard Libby and his team at the University of Chicago. And get this, it was so revolutionary it actually earned him a Nobel Prize. The basic idea is to measure the decay of a specific radioactive version, or what scientists call an isotope, of carbon. And that isotope is carbon-14. Okay, let's follow the journey of the special carbon atom. It all kicks off way up in the atmosphere, where cosmic rays are constantly zapping atoms and creating carbon-14. Then plants, they breathe this stuff in during photosynthesis. And then, of course, animals, and that includes us, we eat those plants. So as long as something is alive, it's constantly taking in new carbon-14, keeping the amount inside it perfectly balanced with the atmosphere. But the moment it dies, that process stops cold. And that right there, that's when the clock starts ticking. And that clock, it ticks at a very, very specific rate. This number you see, 5,730 years, that is the half-life of carbon-14. What that means is that for every 5,730 years that pass, exactly half of the carbon-14 atoms in that dead thing will have decayed away. So by measuring what's left, scientists can work backwards and figure out pretty precisely when it died. Pretty cool, right? It's such an elegant, powerful idea. But, science is never really that straightforward. Pretty soon after Libby's big discovery, researchers started finding a few wrinkles in the whole method. It turned out this seemingly perfect clock was actually a little bit wobbly. You see, Libby's whole theory was built on two really big assumptions that, well, they weren't quite right. First, he assumed the amount of carbon-14 in the air has always been the same, but we now know it actually fluctuates. It changes because of cosmic rays, shifts in the Earth's magnetic field, and even pollution from burning fossil fuels, something called the Seuss effect. Second, his original calculation for the half-life was just a little bit off. The more accurate number we use today is that 5,730 years. So how in the world do you fix a wobbly clock? Simple. You calibrate it against a much more reliable one. And in this case, the hero of our story is dendrochronology, or, tree ring dating. Scientists can take samples from super old trees. Then they match the ring patterns from those dead trees with younger ones, kind of like you see here. By overlapping all these patterns, they can build this amazing, unbroken master calendar that goes back thousands and thousands of years. And since they have a known date for every single ring, they can measure its carbon-14 and create these super detailed calibration curves to fix the carbon clock's wobble for pretty much any point in history. So, the wobble was fixed, the clock got calibrated, and for decades, that was pretty much the end of the story. But recently, a much deeper, much more startling question has started to come out of the world of physics, one that challenges the very foundation of this entire method. The entire system, the whole idea of radioactive dating, is built on what we thought was a fundamental rule of physics, that radioactive decay is random, but on average, it's totally unchangeable. It's supposed to be a fundamental constant of nature. But what if it's not? What if something out there could actually influence the tick-tock of the atomic clock itself? Now, this isn't just some wild theory. We're talking about real data from really respected places, like Brookhaven National Lab in the US and the PTB in Germany. And what they found is evidence of these small but very clear annual variations in the measured decay rates of some radioactive elements. Something seems to be causing them to speed up and slow down in a regular cycle. And this is where the mystery gets even deeper. This weird effect isn't happening to everything. If you look at this table, you can see that isotopes like silicon-32, they show these yearly variations. Manganese-54 even seem to change its decay rate because of a big solar storm. But then you've got others like cesium-137 where nothing happens. And crucially for our story, the same is true for carbon-14. So far, its decay rate appears to be rock solid, which is why radiocarbon dating is still so reliable. So what in the world could be causing this? I mean, the potential explanations are straight out of science fiction. Could it be neutrinos, these tiny little ghost particles streaming from the sun that are somehow interacting with atoms in a way we just don't understand? Could it be invisible dark matter passing through the Earth? Or maybe some other cosmic force we haven't even discovered yet? The honest answer is we just don't know. And that's what makes this such an incredibly exciting frontier of research.
But look, even with all these mind-bending questions happening at the very edge of physics, it's so important to remember that here on the ground, for archaeologists, radiocarbon dating has been, and absolutely continues to be, a total game changer. The impact has just been immense. It's given us dates for the Dead Sea Scrolls, it's helped clear up the timeline of ancient Egyptian dynasties, it's aged prehistoric art on remote islands, tracked the migration of early humans, and it's even weighed in on really controversial relics like the Shroud of Turin. It has fundamentally reshaped our entire understanding of the human story. Let's look at a concrete example of this. For years and years, the timeline for the Aegean Bronze Age was based on comparing styles of pottery. And that method put the start of a key period right around 1600 BC. But as this chart shows, when they applied radiocarbon dating, the results pushed that date back by nearly 100 years, to around 1680 BC. Now, a shift like that might not sound huge, but it forces historians to completely rethink everything about trade routes and cultural connections between ancient civilizations. It's a huge deal. And that brings us to maybe the most important takeaway of all. Radiocarbon dating isn't some magic bullet. Its real power is unlocked when you use it alongside other methods, like studying the layers of soil, which is called stratigraphy, or analyzing styles of artifacts. When you put them all together, you get a much stronger, much more reliable picture of the past. So, after this whole journey, from a simple, elegant idea all the way to the wild frontiers of physics, what have we really learned? Well, it's about a lot more than just carbon atoms. It's really about the nature of knowledge itself. There's this quote from one of our sources that just perfectly nails it. By finding the wrinkles in radiocarbon dating, by discovering its limits and its potential unsteadiness, we haven't made it weaker. We've actually made it stronger, more precise, and more reliable. Questioning our tools is exactly how we make them better. And all of this leaves us with one last, really fascinating question to think about. The story of radiocarbon dating shows us that even our most basic assumptions, like the idea that radioactive decay is a constant, are fair game for scientists to question. It's this powerful reminder that science isn't just a book of facts. It's a dynamic, always evolving process of discovery. And if a constant of nature can be questioned, what other bedrock truths are just waiting out there to be explored?